as Betsy just said, this is really just going to be a result of a 3-year scientific study about what are the scales and reliability of a wind and solar energy system. There's a debate. In fact, it's very often you read people who say, you know, I set up this wind and solar in a small area, and sure enough, during the night, the wind died, and therefore, this really doesn't work. I saw an engineering study where the person said, I assume the scale of weather is 100 kilometers. So I invite that person to look at the daily weather map at night. It's not 100 kilometers. And as director of the Earth System Research Laboratory, we have 600 people and a lot of knowledge of weather over 40 years, and really thought, let's actually see if we can get a quantitative and careful answer about the scales and reliability of wind and solar energy systems. So we've been working on that for 3 years, and I'm going to show you the results of that study. So here's one example where a person talks about the geographic characteristics of wind and solar energy. Wind's unpredictability means it truly has no generating capacity value, and it won't displace any coal or natural gas. Grid reserve margins require that you are able to back it up, and this is bringing up 2 points. One of them is what are the scales at which you need in order you do get less variability, and there's another concept in there called rampiness, where if things change too fast, the grid authority's got to be able to catch up with that. So we, and I want to say there's some really outstanding work done in various parts of the field by people who kind of say the opposite. Mark Z. Jacobson has got a lot of papers out that kind of say, oh yeah, this will work. But again, what we had was the benefit of a laboratory that knows a lot about weather, and just down the road, the National Renewable Energy Lab. In fact, I didn't even want to show this because I knew Dan would get worried when he saw this. But so what did we do? First thing we did is we didn't use a weather model. I've seen people using weather prediction models and thinking that that represents the real world. There's a distinction with a weather assimilation model. So an assimilation model is something that you keep as close to the real atmosphere using all your observations as you can. And anybody that thinks you can get a reasonable climatology for wind and solar out of just running a super high resolution model is wrong. So we used something called the 13 kilometer rapid update cycle. It's actually what's used for aviation. It's the operational weather model used in the United States. And we know a lot about it because we built it. We did it for the continental US, and we had each of 3 years, we collected data for every 15 minutes, ended up with 16 billion points of data, quality controlled, and as far as I'm concerned, far and away the best data set for looking at wind and solar energy. So that's step one. Step two is we had a system to design, and it was based on the idea that you use optimization techniques. We use linear programming to essentially allow a design of a system over any spatial scale you want. The biggest spatial scale we looked at is the US 48 states. And essentially the way this optimization works, and I'll show you a little bit of the math, I won't crush you with it, but there is kind of a nice way to look at it. Essentially, this optimization allows you to put wind and solar energy wherever you want, but it uses a cost optimization to find out where they should go in a domain of any size. Now, of course, if you're running wind and solar, whatever domain, whether it's sort of a small balancing area the size of a US state or whether it's the whole 48 states, there are times when you aren't going to meet load or demand. And so this system uses natural gas backup, just like our current system does. Our current system basically, especially in summer months, has to meet variable demand over the US, and this one does the same thing. We also assumed that we would maintain our existing nuclear and hydro. Finally, we projected both costs and electricity demand to 2030. So that's the study. I just want to talk a little bit about what an assimilation model is. This is the rapid update cycle. The thing to notice about this is that it's continually anchored to the real world. So we take all the satellite data, we take literally as many as 10,000 aircraft observations per hour, thousands, tens of thousands of surface observations, satellite data for clouds. They all go into a dynamic model which makes them consistent with each other. So as far as we're concerned, this is the state of the art of knowing what wind and solar resources are there as a function of space. That's what we use. We wanted to make it realistic, so we didn't say, well, you can put a wind turbine in the middle of Times Square in New York City. You've actually got to see where there are land that you can use. So we classified both for wind and for utility PV, concentrated solar power, over the country where you can put things. You can't put them in national parks, you can't put them on steep mountainsides and that kind of thing. So we used realistic data for where they could go. Then after all that was done, we ran our data to see what it showed. So the first thing that this is just illustrative, because this isn't the optimization, this is just saying, okay, what is the capacity factor? What is the availability of power? Say you have a 1 megawatt generator. If that's basically available half the time, the capacity factor would be 0.5. So what we see in wind is what I think people are quite aware of, and that is there's a big part of central US that has pretty high capacity factors, really quite good, and you can actually see the details there. I'm from eastern Montana, and the rivers and so on are quite clear there. And my friend's uncle's ranch out near Ritchie, Montana, it looks really windy in this thing, and that's really the way it is. It's just how it is. So that's the capacity factor for wind. And similarly, here's a capacity factor for concentrated solar power, which shows again what a lot of people would think, and that is the desert Southwest is a huge resource for solar power. And by the way, there was an interesting thing in one of the charts that Dan showed, which is when you look at wind, there is more of a finite resource when you get really large usage than there is for solar. Solar's got a huge potential, and that's a complicated story that I'm going to come back to in a minute. So we wanted to be realistic. This is a graph every hour of U.S. electricity load. So the U.S. is using 400 to 500 gigawatts. And those little blue lines and notches, you actually are looking through the year. Those notches are actually the weekends. So we use less power on the weekends in the U.S. And you also notice spring and fall, it's a little bit lower. And the big peak up there above 700 gigawatts is in the middle of a hot summer afternoon. So when we do this optimization, we're going to go through hour by hour through the whole year and actually optimize the generation design based on actual load and actual places where you can really put the wind and solar. Now it starts to get interesting. This is wind versus load covariance. So there's a lot of people looking for a flat place with a lot of wind and saying, boy, that must be where to put a wind turbine and I'll make a lot of money. But that isn't necessarily so, especially if you recognize that if we're going to optimize over larger areas, it matters what the load is over larger areas. So what we have here is wind versus load covariance for the 48 state domain. And what it shows is that those blue areas in the Midwest are areas where it's highly anti-correlated with load. When the wind blows in the middle of the night is when you don't need it so much because the air conditioners aren't going. And when the wind isn't blowing in the middle of the day is when you really need the electricity. So this little diagram shows you something kind of simply, and that is there's a lot of the U.S., essentially east of about 100 west, that isn't very well correlated. The west, interestingly, and even the high plains are actually pretty good. So it isn't good enough to just say, where's the wind? If you're going to design a system, you want to design it so that you're getting the resources that are available when you need them. Now, notice this is on the same scale as the wind, and you really don't have anything that's anti-correlated. That's because, even though we use lights at night, our power usage is really during the day. That's when it is highest. So essentially, the solar versus load covariance, what you see is the west is highly covariant. In other words, it corresponds to when you need power. I'll tell you something really interesting because we looked at this data a lot over the last 3 years. If you look at that area of the Southwest, essentially the sun is straight over California at about noon, and that's 3 p.m. where the maximum air conditioning load in the eastern United States is. So that 3-hour difference makes it perfect. And those are the kind of things that we wanted to unsort with this study. In other words, let's look at the actual quantitative systems as they vary by scale. All right, here's this equation which I don't want anybody to get math anxiety. It's not that complicated, and I'll just explain it fairly easily. Essentially, we're going to design a system over the whole country. So what these little eyes are, is this is for every 13-kilometer rectangle over the whole country, and essentially we're taking the price of putting in the wind turbine and deciding how many wind turbines to put in each one of those little rectangles. We limit it to 1 per square kilometer, so we don't have high density. And so we minimize the total number of wind turbines and utility, 100 megawatt utility plants. And every time step, we're going through this time step, which is K. Every time step, if this sum of this linear programming designed set of wind and solar plants don't have enough, then we actually add in the gas cost. The G is for gas. But it's subject to, at every hour through the whole year, we have to meet demand. So we're using like the dot product. We're sort of saying, we're going to design a system. It starts off, it has no solar plants, no wind, and keeps adding them, but it adds them where it gets the most effective use out of them, not sort of just in general, but according to the total cost for the year. And so we used the GAMS software, Cplex, and we ran literally thousands of these optimizations, and I'm going to show you some results. Here's result 1. This pretty much is how it almost always looks. This system wants to put wind through the plains. It doesn't want to put it out in the Midwest. These light blues are saying, well, there's a little bit there. In this particular one, there's not a lot of offshore wind in the East Coast. That's partly because we do have cost estimates in this stuff, and we're very conservative on our cost estimates. We're using EIA best cost estimates, and this particular one was fairly high in terms of the offshore cost of wind. So it puts lots of wind, these blue things, sort of maxes out these windy areas in the high plains. And the only other thing it does is it puts a whole lot of solar in Southern California. First question everybody asks is, oh my gosh, what about Arizona and Utah and Nevada? We were really puzzled by that too. We went to the data. The data actually showed that the problem is when you need it the most, Arizona, in sort of a July afternoon, Arizona's got its summer monsoon going and there's too much cirrus overcast. And that cirrus overcast showed up very nicely in our data set, and it's just flat is there. It's basically stopping the power when you need it the most. So this is a national design where it's been optimized, and it basically says East Coast a little, lots of wind in the plains, and lots of Southern California solar is optimal. All right, just one graph. I'm only going to look at the blue part of the graph. So what we're looking at here is the cost of natural gas. So remember how this thing works. That system that I just showed you, and I should have said this, this system basically delivers U.S. Power about 70% from wind and solar, and 15% from natural gas, and 15% from hydro and nuclear. That's what this system delivers. So your next question is, yeah, I'm sure, how much is the cost? And I'm going to come back to the spatial aspect in a second. Well, the cost is interesting. So we ran this optimization model a couple hundred times to get a good curve. And essentially, if your cost of natural gas is zero, it uses all natural gas. However, it reaches a point, this is in cost in dollars per million BTUs, it reaches a point where there's like a hysteresis. That is, where the wind and solar all at once becomes competitive in our best areas. So essentially what that says is that at today's prices for natural gas, it says really straight up levelized cost, we probably shouldn't be using much. If you take the best estimate, the lowest cost for natural gas in 2005, in 2035, essentially this system says that given those costs, that you're up on this other part of the curve where you want to have a lot of wind and solar. Now I want to come back to one more thing. That is a question of scale. So the question is, this one is using the whole 48 states, and it's obvious that you've got to think about transmission systems and grid integration if you're going to do something like this. Essentially, the cost of power out of North Dakota is 1/4 the cost. If you go, to the Willamette Valley of Oregon, you're going to pay 5 times more for wind and solar in Oregon than you are in North Dakota. So it's like everything. You put the gold mine where the gold is, you put your wind and solar where it is, but then you got to deal with a transmission system. My own opinion is the United States has faced these transformations before. Very nice scene in Stephen Ambrose's book of President Lincoln thinking about transcontinental railroads. This nation needs transcontinental railroads. When we think about the interstate highway system in the U.S. and every nation, I think, the nations around the world, we took a look, I'm not going to show it, we took a look at the European Union, we took a look at Russia, India, and China. They all have this same thing. There's a place where if you do large-scale integration and bring your grid up to it, this can be very cost-effective in the kind of prices that we're likely to see for wind and solar and for fossil fuels during the coming few decades. So I think in the problem that has to be solved is basically grid and transmission. So just a quick summary of the results of the study. I didn't go into this much, but it turns out that you get pretty reliable and smoothed power for an area about half the size of continental US, about 5 million square kilometers, and that's pretty true globally. We looked at our global model, and that's pretty much it. That's the size you need. The location of optimal generating capacity means you got to have the transmission systems. The wind and solar generation for an optimal national system is really, you're not going to arrive there by just an ad hoc bottom-up approach. It needs to be thought of as a large-scale problem. And even using conservative cost estimates, a national system a few decades from now could be supplying a large amount of wind and solar power more effectively and probably cheaper than the fossil fuels will be delivering at that time. And I think I'll stop there.